Hello and welcome. Why couldn't the bike stand up? Because it was too tired. In this video we're going to learn about antiderivatives, which have nothing to do with bikes and being tired. It's about reversing the process of finding the derivative. Let's get started. So sometimes we know the derivative of a function and we're trying to find the original function. For example, trying to find the position function if we know the velocity function. This reverse process of differentiating is called antidifferentiating, or sometimes called finding the antiderivative. So in our definition of antiderivative, we'll say big F is an antiderivative of little f on an interval I if the derivative of big F is equal to little f for all x in the interval I. So big F is an antiderivative of little f if the derivative of big F is equal to little f. This big F right here, usually capital letters are used to denote an antiderivative, and the lowercase letters would be used for just regular old functions. So example 1 says find an antiderivative for each of the following functions. Little f of x equals 2x. Well, here we can write an antiderivative of 2x would be x squared. And off to the right we can say this is true since if we turn back around and take the derivative of big F, the derivative of our antiderivative, we get back to little f. So if we wanted to draw a picture of this, we could say, here's little f. We took an antiderivative of little f to get big F. And then we turned back around and took the derivative of big F to get to little f. So finding the antiderivative is just the reverse process of finding the derivative. What would be the antiderivative of g of x equals cosine x? We'll call that big G of x. If you said sine of x, that would be correct, or sine x. And that's because if we turn back around and we take the derivative, we'll get cosine x. What about h of x equals 1 over x plus 2e to the 2x? What would be an antiderivative big H of x of that? Well, antiderivative for ln x, for 1 over x, would be, just gave it away, would be ln x, because the derivative of ln x is 1 over x. What about for the 2e to the 2x? If you said e to the 2x, then that would be correct. Turning back around, if we took the derivative of e to the 2x, it would be e to the 2x, but then by the chain rule, times the derivative of 2x, which is 2. That's where this 2 would be coming from. So that's an antiderivative of h of x. And we can write, since if we turn back around and we take the derivative, we get back to little h. Now what we've done in example 1 is find particular functions that are the antiderivative of these little functions. But suppose in the first example here, we instead wrote x squared plus 2. X squared plus 2. Well, that would be another antiderivative of 2x. Because if we turned back around and we took the derivative of x squared plus 2, we would still get 2x. The constant just disappears when we turn back around and take the derivative. In fact, we could put any constant we want there, and when we take the derivative of it to check our work, then it just disappears. It goes to 0. So what we could do is we could say these are particular antiderivatives, but the general antiderivative, the most general one that would include all the possible antiderivatives of 2x, would be x squared plus c. So the c here is representing just some constant. It could be like the 2 that we mentioned a second ago. It could be 5. It could be -10. It could be pi, just as long as it's a constant. Because then if we take the derivative of x squared plus a constant, the derivative of that constant becomes 0, and the derivative of x squared is 2x. So x squared plus c is the general antiderivative of 2x. Now, in the picture on the right, we've got many different particular antiderivatives of 2x. Each one of these is a particular antiderivative of 2x. For example, this one on the bottom, the x squared minus 2, that's the particular antiderivative of 2x that's in the form x squared plus c, where c is equal to -2. Right? If we replace c with -2, we get x squared minus 2, and that's what this curve is. Right here would be c equals -1 for the second curve, and then c equals 0 for the next curve, and then c equals 1, and c equals 2. So the picture is just showing 5 members of that family of curves, x squared plus c. Now, of course, there are an infinite number of them, because again, you could go 3, 4, 5. There are parabolas inside in between these two, like c equals 1.5, c equals pi, as we said. But this is just showing 5 members of that family. Now, if you were given a point on the plane, then that would pick out one of the members of the family. So this is what's happening with example 2. It says, find the antiderivative of 3x squared that satisfies big F of 1 equals -1. So once we find the general antiderivative, we're going to have this extra condition to satisfy, which is big F of 1 equals -1. Another way of thinking about this big F of 1 equals -1 is to think it represents the point 1, -1, right? The input x is 1, the output is y, which is -1. So looking briefly ahead, we're going to find out that the antiderivative is x cubed plus c, kind of giving the answer away. And so this is going to be a whole family of these curves, these cubic curves, x cubed, but shifted up and down to produce the other ones. And we're going to find the member of that infinite family of curves that goes through the point 1, -1. That would make it satisfy big F of 1 equals -1. Let's see how this would look algebraically, though. So it says find the antiderivative of 3x squared that satisfies this condition. So first we start with the most general antiderivative. The general antiderivative. What would that be for 3x squared? What would be the general antiderivative? Pretend like I didn't just tell you the answer a moment ago. So if you said x cubed and then plus c, then that would be correct. Oh boy. All right, so that's the general antiderivative. If we turn back around and we take the derivative of that, we get back to 3x squared. We can always retrace our steps and make sure that we got the correct antiderivative. Now let's do the algebra work to figure out the exact member of this family of curves that also goes through this point 1, -1. In other words, it also satisfies this equation. What this is going to do is allow us to find c, which is, as we mentioned, identifying a particular member of the family. So we can start by writing out big F of 1 equals -1. Now, big F of 1, we have a function now. We have big F of x in general, it's x cubed plus c. So big F of 1 would be 1 cubed plus c. And then I'll just copy down the equals -1. Now we can solve for c. Subtract the 1 over, and we've got c equals -2. So big F of x is x cubed minus 2. That's the member of the family that goes through that point 1, -1. So one thing I wanted to mention before we go on is that the plus c is always taking whatever antiderivative you have and shifting it up and down. So it's going to fill out the plane. No matter what kind of function you have for the antiderivative, the plus c will make that cover the whole plane. It's going to give you a whole bunch of solutions that'll cover the plane. A whole bunch of functions that'll cover the plane. Let's spend a little bit of time practicing with just the little algebraic parts, like the how do we find the antiderivative of 3x squared and things like that. So we have a table of functions, and on the right side we're going to try to find the general antiderivative for these functions. So what would be the general antiderivative of x to the n in general? So this could be x cubed, x to the fourth, x to the fifth. What would be the general antiderivative of x to the n? So this one's tricky, but if you said x to the n plus 1 over n plus 1 plus c, then that would be correct. Now there's a side note here, which is that n can't be equal to -1. We'll explain that in just a moment. But the reason that this is the general antiderivative of x to the n is that if you turn back around and you think about using the power rule, the exponent would the n plus 1 exponent would multiply to the front, cancel off this n plus 1 on the bottom, and then you would subtract 1 from the exponent, so n plus 1 minus 1, and get an exponent of n. So when you turn back around, you end up getting x to the n. It kind of makes sense, because if you think about the power rule, let me do the power rule off to the side. If you think about the power rule, just going regular derivative, going straight forward, you multiply the exponent in front, and then you subtract 1 from the exponent. Going the opposite direction, it makes sense that you would do the opposite things in the opposite order. So add 1 to the exponent, and then divide by the exponent. Instead of multiplying by the exponent and then subtracting 1 from the exponent, we'll add 1 to the exponent, and then divide by that exponent. It's doing the opposite things in the opposite order. And again, we can double check it. We can check to make sure that x to the n plus 1 over n plus 1, that if we take the derivative of that, we'll get back to x to the n. Now again, the plus c there is to make the most general antiderivative. The only case where this doesn't work is when n is equal to -1. If n is equal to -1, then you have x to the 0, which is 1, which then it's hard to know what's going on there exactly. I mean, what if x is equal to 0 too? Not to mention that issue. So, and in fact, when x is when n is -1, then you have 1 over x to the -1, which is 1 over x, and that one has a separate antiderivative that we're going to cover down at the bottom here. But let's move on. What about the antiderivative, the most general antiderivative for sine x? What would that be? So if you said negative cosine x, that would be correct. Well, plus c, to make it general. Let's check. If we take the derivative of negative cosine x, does that get you back to sine x? Yes, because there's going to be an extra negative that pops out when you take the derivative of cosine x, right? Derivative of cosine x is negative sine x, so that negative and this negative make it positive positive sine x. So when you're doing the antiderivative, then it's kind of the opposite of those c cosine, the c trig functions. Normally the derivatives of the c trig functions like cosine, cosecant, and cotangent have negative signs in front of them. When you're reversing that process, then kind of the opposite happens. What about the antiderivative for cosine x? So if you said sine x plus c, that would be correct, because the derivative of sine x is cosine x. How about the antiderivative for secant squared x? If you said tangent x plus c, then that would be correct. Secant squared x is the result of taking the derivative of tangent x. So if we want to reverse that process, then the antiderivative of secant squared x is tangent x, because turning back around, the derivative of tangent x is secant squared x. Similarly, antiderivative for cosecant squared x will be negative cotangent x. Antiderivative for secant x tangent x will be secant x. And then cosecant x cotangent x, the antiderivative will be negative cosecant x. Again, you can double check by taking the derivatives of the right column and making sure that you get the left column. What about e to the x? Antiderivative of e to the x? E to the x plus c, because the derivative of e to the x is e to the x. What about the antiderivative for 1 over x? So if you said ln x, that would be correct, plus c, of course. But here we're going to do even more than that. We're going to put absolute value bars around the x, because it turns out that that's the most general antiderivative for 1 over x. It gives you the widest domain possible. If you recall from an earlier packet or earlier lesson, we had talked about this very briefly. We said that you can say that the derivative of natural log of the absolute value of x ends up being 1 over x. We expanded the derivative of ln x to the derivative of ln absolute value of x. And we mentioned at that time that it would happen in a future packet that that would be brought up again, and here it is. So this way, both of these functions have a domain of all real numbers except for 0. When you put those absolute value bars around, now the ln absolute value of x can accept positive and negative numbers. Still can't accept 0, but it can accept positive and negative numbers. And it just turns out that the derivative of the natural log of absolute value of x is 1 over x. The rate at which this function changes is 1 over x. So when we're trying to find the antiderivative of 1 over x, the most general one, we're going to write ln absolute value of x. A couple other ones. The antiderivative for 1 over the square root of 1 minus x squared, that's going to be inverse sine x plus c. And then 1 over 1 plus x squared will be inverse tangent x plus c. Then a to the x, the antiderivative of that will be a to the x over ln a plus c. So what I'd like you to do between this video and the next video is practice with these. Try to cover up the right-hand column and see if you can write out the antiderivatives. It's going to be very important, not only in this class, but also in your future calculus classes, to get very familiar with antiderivatives. So thank you for watching, and I'll see you in the next video.